Welcome back. We are now on Unit 2 called Derivatives. We are on Lesson 1, Derivatives of Polynomials. So in the previous unit, you learned that the instantaneous rate of change is represented by the slope of the tangent at a point on the curve. You also learned that you can determine its value by taking the derivative of the function using first principles definition of the derivative. I just want to remind you what a derivative actually is. So what is a derivative? Well, a derivative is the instantaneous rate of change of a function. It is the slope of the tangent of a line at a point, at a specific point. And just to highlight, remember it is a slope of a line, okay? Of the tangent. So we're first going to study the derivatives rules and techniques for simple polynomials. So here is a table of all of the simple rules, okay? So if you have a constant, remember, think about what a constant actually is. It's just a straight line, okay? So how does it change? It doesn't change at all. So that means that the derivative will be 0. So if a function is equal to a constant, the derivative is equal to 0 because there's no change. So here's what we sort of looked at before. We're going to look at this a little bit closer. As I've mentioned, if you have a power function, so just a function that is a variable with an integer exponent of n, okay? What we found earlier that it actually the derivative was 1 lower, the exponent was 1 lower than the original function. And you also multiply that by n. Okay, and here it is as well in Leibniz notation. So with a constant multiple rule, if you have a constant in front of a function of any kind, you would just put that constant up front and take the derivative of just the function. Okay. Sum rule, if you have functions that are simple polynomials that are an addition or even a subtraction to each other, that you take the derivative of each and then add them to each other. Okay. And those are sort of the simple ones. Difference rules, the same thing as the sum rule. And we'll come back to that. We'll take a look at these a little bit closer. Okay, let's take a look at this example. So in this example, we want to differentiate each function using the derivatives rules. So starting with part A, our function is f of x, x to the exponent of 5, plus 8. Okay, so in this case, what we can say is we have two functions that are a sum of each other. So I'm going to take the derivative of each of them separately and add them to one another. Okay, so I just want to make a little side note because I don't think we're used to doing these yet. So if you had something like this, okay, that is a power function. Remember, it's n. Okay, so if we wanted to find the derivative, it's just n, which is your exponent, so n times n, x, and you take the exponent and you minus it by 1. So it would be 4, and that is the derivative of x to the exponent 5. Okay, so it's 5x to the exponent 4 plus 0. So our derivative is then just x prime at x is equal to 5x to the exponent 4. Okay, so B part. B part, our function is f at x is equal to, no, it was y, but I'm just changing it to f at x, is equal to the cubed root of x squared. How are we going to do this one? You could use first principles, but why would you now that you know your new rules? So what I'm going to do first is actually change this to exponents. So when you use your exponent rules, okay, so remember that a radical just works out. If you want, I can do this step by step and then I will start skipping some steps later on. Okay, so a radical, whatever that is in this radical there will go in the denominator of the fractionated exponent. Okay, so something to review if you need to review your exponents, and I can post, if you need, I can post a few things there if you need to review. And then you just now simplify even further by multiplying, so 2 over 3. Okay, so now what we can do is actually find our derivative. Okay, f prime at x, and remember, it is, just a little side note, is equal to n of x and minus 1, okay? And this will be just something that you would find intuitive, that you're going to be doing this all the time, and you won't even need to think of it this way. But for now, I just want to remind you, so it'll be 2 over 3 x, okay? So 2 over 3 minus 1, okay? One way to look at it, 2 over 3 minus 3 over 3 is equal to negative 1 over 3, okay? So negative 1 over 3 is our exponent. So just for good practice, we can say that I would first do this 1 over this third root of x, okay? Now, a little hard to look at. I'm going to rewrite this. So 2 over 3. I just want to rewrite it so you actually see what that number is. Right there, that's a 3. Okay, so what we've done is gone the opposite now. So up here, it was easy for us to leave it into exponential form, but I want you to practice simplifying because it's good algebra skills. Okay, so that'll be just 2 over 3 as the integer out front, and it's the third root of x. And because of this negative exponent, that's why we have it as 1 over. Remember, when you have a negative exponent, to turn it to a positive exponent, we would just put it in the denominator, okay? And that would be our derivative. And now that is much easier than using first principles. Okay, part C, f of x is equal to negative 1 over x to the exponent 5. Okay, so here we have a fractionated function with our variable in the denominator. Again, it is easier for us to work with exponents. Okay, so I'm going to change this, use my exponent rules again. Just as a reminder, and we looked at this in the last one as well, but just as a reminder, okay, 1 over x to the exponent a is the same as saying 1 over, x to the exponent negative a. There we go. Okay, just ignore that. There we go. X to the negative a. Okay, so let's change this over first because I think that'll make it easier. These are just little tricks that you're going to come up with and develop on your own, okay? Oops, I just rewrote it again. Negative 1 times x to the negative 5. Okay, we can drop this negative 1 part. So it's just negative x to the negative exponent 5. Okay. All right, so now we can actually take the derivative. F primed at x, that is equal to, my marker is starting to go. Okay, so remember that you wanted to take your exponent and bring it out front. So what it is negative 1 times negative 5, so that's just positive 5x. Remember, it's negative 5 minus 1, okay? So it's negative 6. So to the negative exponent, negative 6. Again, I want you to express all of your answers in positive exponents and without fractional exponents as well. Just for good practice, it is good for the algebra skills. 5, okay, x to the exponent 6. Okay, on a test, on an assignment, I will not accept negative exponents. They all have to be in positive exponent form. Okay, so that was nice practice. Let's move on to harder questions. So we have part D, E, and I'm not sure why this is C, but we'll say that's E. So D, E, and then F, okay? So these are a little bit more complicated, but again, don't get too confused. It is basically the same thing that we've been doing before. We're just going to take a look at some algebra skills that we're going to use in order to simplify this and to make it a little bit easier on us. Okay, so let's take a look at D. D, g of x is equal to negative 8x squared plus 2 the square root of x minus 4. Okay, so we've got 3 terms. So what we can do is actually find the derivative of each of those terms and add them together because our sum rule. What you'll notice here, though, we've got a radical. Okay, so I would first change any radicals or any fractions that have the variable in the denominator into exponential form. So 2x to the 1/2, okay, minus 4. Okay, so now we can find g primed at x, each term separately. So negative 16x plus 2 times 1/2, okay, which, not sure why you can't see that. There we go, is just 1x. Remember, 1/2, and it's always minus 1 no matter what. So 1 over 2 minus 2 over 2 is equal to negative 1 over 2. Okay, so x to the negative 1 over 2 minus 0. And I'm just going to drop the 4. Okay, simplifying a little bit more by changing your negative exponent. So the first step I always do is change the negative exponent first, and then we'll change the fractional exponent. X plus 1 over x to the 1/2. So that takes care of my my negative exponent. Is equal to negative 16x plus 1 over the square root of x. And that's a proper answer. In part E, we have h of x is equal to negative 4x cubed plus 8x squared over 4x to the exponent 6. Okay, so that looks a little bit sloppy. What we're going to do, what do you think we need to do? Think about it for a second. Okay, what I'm going to do, okay, is I'm going to factor the numerator. So I'm going to factor out of 4 and my highest exponent, or sorry, my lowest exponent of the variable. So that leaves me with x minus x plus 2. Okay, all over 4 x to the exponent 6. Okay, so what that leaves me with, I'm going to cancel out the 4s. 2 with 2 of those will leave me 4 after I subtract 2 from 6. So what I'm left with in the numerator, it's going to rewrite this, is x to the exponent 4. Okay, so h of x. I'm not quite done simplifying it, so let's go h of x. And this we can change into x to the negative 4. Okay, just to bring it to the numerator. Then I'm going to multiply that in. So remember, this x has an exponent 1. So when you multiply, you just add your exponents. Okay, so it's negative x to the negative 3 plus 2 exponent to the negative 4, like so. Okay, so now that we have h of x, we can actually go ahead and find our derivative. So let's do that over here. So h primed at x is equal to 3x to the negative 4 minus 8x to the exponent negative 5. Okay, let's double check that. So bring it forward. Okay, and remember, answers are always in positive exponents. So what we have then is 3 over x to the exponent 4 minus 8x to the exponent 5. And I would probably just leave that as so. And that's a 5 there. Okay. All right, so part F, y is equal to 3x minus 2 times 5 plus 4x. Okay, so I'm going to use Leibniz notation in this one just to get you used to it. Okay, so what can I do here? I don't know that many rules for multiplication quite yet, but you will learn it in the next lesson. Okay, so what do I need to do? When I see this, okay, I always want to FOIL it. I don't know about you. I don't know if anyone has learned FOIL. Hopefully you have. It's a way of expanding a product of two binomials. So the first, okay, so I'm going to multiply the first two, the outside, inside, last. Okay, so that's the first thing I'm going to do in order to get this in a nice form that I can use. And you might have some shortcuts, which is fine. I'm just going to do it the long way just as an example. Okay. Okay, so just to simplify, 12 x squared (7x minus 10). Okay, and that's much easier to work with. So dy by dx is then equal to 24x plus 7. Okay, and that's our derivative. Let's move on to our final example. Example number 2. Determine the slope of the tangent to the curve of y is equal to -6, x to the exponent 4 plus 2, x to the exponent 3 plus 5 at the point -1 and -3. Okay, so what is it really asking? It's asking us to find the slope of the tangent. It's a slope, right? So, well, the slope of the tangent is the derivative. It's the derivative of this function at that point. So we're going to evaluate it at that point. So our first step in example number 2a is to find the derivative of this. Okay, so of our function. So I'm going to use Leibniz notation. Dy by dx is equal to then, okay, so bring the 6 out front, -24 x to the exponent 3 plus 6 x squared. Okay, and now we're going to evaluate it, okay, at this point. And really all that matters is going to be the x. So it would be x is equal to -1. Okay, so dy by dx when x is equal to -1. Okay, and I'm just going to sub in -1 wherever there is an x. 24 -1 to the exponent 3 plus 6 -1. It's 2, and my pen seems to be running out. Which then just leaves us with -24, okay, because this will just be -1, so that'll be positive 24, and plus 6. Okay, so that'll be 30. Just to finish off, therefore, the slope of the tangent is 30, okay, at -1 and -3, okay? So part B wants us to determine the equation of the tangent at this point, okay? So taking a look at B, remember that the equation for a line in slope-intercept form is y is equal to mx plus b. And remember, we need to find m and we need to find b. So our m in this case, we just found it, at the point is 30, okay? And we know our point x is equal to -1, y is equal to -3. So to finish off, we need to find what b is. Okay, so let's sub everything into our equation and find b. So over here, we'll say, let's start again, -3 is equal to 30 times -1 plus b. Okay, so isolating for b, we're going to say that b, I'm going to bring everything over to the other side, so it's 3. So 30 times -1 is -30, but when I switch to the other side, it is positive 30. So b then is equal to 27. Okay, so subbing everything back in, we're going to come up with the equation, the general equation of 30x plus 27. Okay, so therefore, the equation is y is equal to 30x plus 27. And that would be our answer. And that just about sums up our lesson for today. One last thing is we want to check our learning. So in today's check our learning, what is the derivative of pi? So we have a is 1, b is pi, c is 0, and d does not exist. So make your decision now. Okay, and our answer is, let's get a nice colorful pen here, C. Okay, 0, because pi is a constant. And that concludes our lesson for today, and we'll see you next time.